Of all the assumptions Bohr made in his model of the hydrogen atom, perhaps the most puzzling is the assumption about the angular momentum of the electron, where L sub n equals mvn Rn, which equals nh divided by 2 pi, where n is an integer. Why should the angular momentum have only those values that are integer multiples of Planck's constant divided by 2 pi? In 1923, 10 years after Bohr's work, de Broglie pointed out that his own theory for the wavelength of a moving particle could provide an answer to this question. In de Broglie's way of thinking, the electron in its circular orbit must be pictured as a particle wave. And like waves traveling on a string, particle waves can lead to standing waves under resonant conditions. Standing waves on a linear string form when the total distance traveled by a wave down the string and back is one wavelength, two wavelengths, or any integer number of wavelengths. The total distance around a Bohr orbit of radius r is the circumference of the orbit, or 2 pi r. By the same reasoning then, the condition for standing particle waves for the electron in a Bohr orbit would be 2 pi r equals n lambda, where n is the number of whole wavelengths that fit into the circumference of the circle. In the case shown here, we show an example of a Bohr orbit with a radius of 4 wavelengths. According to de Broglie, the wavelength in this equation is the de Broglie wavelength of the electron, h divided by p, where p is the magnitude of the electron's momentum and is equal to mv as long as the speed of the electron is much less than the speed of light. The condition for standing particle waves becomes 2 pi r equals nh divided by mv. A rearrangement of this result gives mvr equals nh divided by 2 pi, which is precisely what Bohr assumed for the angular momentum of the electron, Ln. As a macroscopic demonstration, consider a circular loop of plastic cord clamped to a small motor that displaces the cord vertically in periodic fashion, causing waves to propagate along the cord. When the frequency of the agitation is such that the circumference is an integral number of wavelengths, a standing wave is formed around the loop, and we can see the nodes and antinodes. If we now increase the frequency, the wavelength decreases, and more waves can fit in the same circumference. The standing wave now has more nodes and antinodes. De Broglie's explanation of Bohr's assumption about angular momentum emphasizes an important fact, namely that particle waves play a central role in the structure of the atom. Moreover, the theoretical framework of quantum mechanics includes the Schrödinger equation for determining the wave function psi that represents a particle wave. The next section deals with the picture that quantum mechanics gives for atomic structure, a picture that supersedes the Bohr model. In any case, the Bohr expression for the energy levels can be applied when a single electron orbits the nucleus, whereas the theoretical framework of quantum mechanics can be applied in principle to atoms that contain an arbitrary number of electrons.